Welcome back. In this lecture, we are going to see this result of Baire category theorem from topology. We have more or less recalled everything about everything that we need to, everything that we can in the complex function theory. So now we move to some results of topology. So the first result that I would like to consider is the Baire category theorem. So if you are given a topological space X and if E is a subset of X, you say E is dense in X if the closure of E is the entire X. And closure of E means set of all its accumulation and limit points. Now you say a subset of the topological space X is nowhere dense in X if the interior of E closure is empty. Okay, so something like you see, if you take the real line R, then the set of all rationals, which is a subset, or set of all irrationals, which is a subset of R, are dense in R, right? Whereas the set of all natural numbers or set of all integers, these are nowhere dense in the real line. We say a topological space is separable if it contains a countable dense subset. As an example I gave, if R, the real line, is separable. In fact, any Euclidean space is a separable topological space because it has a countable dense subset. You can think of the set of all rationals which is dense and it's countable. And this is true for even in Rn. If you take q power n, it's a countable dense subset of Rn. Now, this is the notion of, suppose you have a metric space X with the metric D, and if E is a subset of X, one can define this notion of distance of the set from any given point. So if X is any element of the metric space, so if little x is any element of the metric space capital X, then the distance of E from X is nothing but the distance between X and Y, where Y is running over all elements of capital X, and the infimum of this number is defined as the distance from X to Y. Basically, this is the from X to Y. From X, you look at the distance between all elements from X to all elements of E, and the distance is precisely the shortest uh, shortest path to reach E. For instance, if you take, since E is a subset of the topology, the metric space X, then if X itself is an element of E closure, then the distance of X to E is 0. Okay, because so X belongs to E or E closure, then the distance from X to E is 0. Now this distance function is actually Lipschitz function. It's actually uniformly continuous function. That's what the statement of this theorem is. So in a metric space, if you have a subset E, then the distance, if you think of this distance function, that is for each X, the function takes the number which is the distance of X from X to E. This is a Lipschitz functions here. Okay, this statement means that the distance function is Lipschitz. In particular, it's a uniformly continuous function. So what is the proof of this? Quickly, so define this function f of x. So for any x in the matrix, any little x in the matrix space of capital X, you define the real valued function f of x is nothing but the distance of x from E. So there are two possibilities for E. Since E is a subset of the matrix space X, E is either dense or it's not dense. If E is dense, then E closure is X, right? In that case, the distance of this function always takes the value 0 because X is always coming from capital X, which is E closure, and this distance is 0. That means this capital F, this distance function is actually the constant function 0, which trivially satisfies the condition that we need to prove, which is the Lipschitz condition. Okay, 0 less than or equal to 0. Sorry, 0 less than or equal to dx comma y. Now, the other possibility is E is not dense in E. If E is not dense in E, then E closure is a proper subset of capital X. Now, by the definition of the distance function, as I said, this distance function is infimum over all x, distance from x to all elements of E. So since this is an infimum, so once you fix an x, once you fix an s, ff, so this fx is the infimum. So if you increment this infimum by some small epsilon, then you can pick a element E from the capital E such that the distance of x to E is less than or equal to this, right? This is by the definition of this distance function. So therefore, because if you have this, I'm just changing the inequality, I mean just bringing the other side here. So minus fx is less than or equal to minus dxe here. So and fy is the infimum over all these elements over all possible e's. So in particular this e, so fy is less than this quantity. So fy minus fx is less than or equal to, this is a quantity bigger than this, and minus fx is precisely this quantity here, and this becomes dyx, this is by the triangle inequality, because dyx is less than or equal to dye is less than or equal to dyx minus dxe, right? So from that triangle inequality, we get that this quantity is dyx. Now, since your epsilon is an arbitrary choice, you have that. Sorry, I'm just running fast. So you have this. Now the same argument can be repeated by interchanging the role of x and y. So whatever we did for x and y here can be done for y and x, right? So this doesn't really matter. So you can actually also show fx minus fy is less than or equal to this, which means mod fy minus fx is less than or equal to this quantity. Now epsilon, as we see, is arbitrary, so we have the Lipschitz continuity property of the distance function, and hence it's continuous. It's also uniformly continuous because of this Lipschitz property. Now, what are first category and second category sets? So, if a subset of a topological space is said to be first category if it is a of countable union of nowhere dense sets. Okay, so that's our first category. Now, what is the second category? Second category is a subset which is not first category. Okay, so a set is either first category or it is second category. First category means it is countable union of nowhere dense sets. Let's start with the theorem about something on the metric space. So if X is a metric space and if UI is a finite collection of dense open sets, then the intersection of this finite collection is also dense in X. So there's a finite intersection of dense open sets. So the finite intersection is also dense in X. So this we can prove easily. Let's go through the proof step by step. So first of all, to show that this U is dense in X, it is enough to show that for any X naught and for any epsilon naught, if you take a ball of radius epsilon naught around X naught, that should intersect U. Density means that, right? So this should intersect for any choice of epsilon naught and X naught in X. So we need to show that. So you start with an X naught and you start with an epsilon naught. Now since U1 is dense, this B epsilon naught X naught intersection U1 is not empty. This is by the density of U1. We need to show the density of U. So by the density of U1, this intersection is non-empty, which means there is a element in this intersection. Let's call that X1. Now X1 is sitting inside this. This is intersection of two open sets, which is open again. So which means X1 is in this open set, which means that there is a ball of radius epsilon 1 which is completely contained in this set. Okay, so once you start with an X naught and epsilon naught, by doing this process using this density of U1, right, you obtain a x1 and an epsilon 1 such that this happens, such that these two happens. X1 belongs to this and this epsilon 1 radius ball centered at x1 is contained in this. So you repeat this procedure. Basically, now that you have x1 and epsilon 1, you repeat the same procedure, whatever you did for x0 and epsilon 0. Okay. So repeating this procedure, now you are going to get using the density of U2, you are going to get a x2 and epsilon 2, such that x2 belongs to this intersection and b epsilon x2 is contained in this ball, contained in this intersection. So by continuing this argument, you will finally see you are going to construct an n number of points in capital X and positive numbers epsilon 1 to epsilon n, such that the epsilon I radius ball centered at xi is contained in epsilon I minus 1 xi minus 1 intersection ui, right? Something from here. And this happens for all I. So just by our construction, xn belongs to this because this is true for all I and xn. So if you look at xn is contained in n minus 1, xn minus 1, un minus 1, and each of these have the inclusion in the bigger space, and so xn is contained in this intersection of this, which is b epsilon naught x naught intersection u. Since x naught and epsilon naught were arbitrary choice, what we have shown is that u is dense in X. Right, so this intersection is non-empty is what we have shown. We have picked the xn from in this intersection. Okay, so now let's prove the main result of this lecture, which is the Baire category theorem. The Baire category theorem says that if you are in a complete metric space and if you have a sequence of dense open subsets, that is a countable collection, then the countable intersection of these dense sets is also dense. So this is precisely the countable version of the previous previous result that we proved which was for the finite collection, right? We said finite intersection of dense open sets is dense in X. So this is the Baire category theorem is basically the countable version of that result, and this is true for complete metric space. So we have this additional hypothesis of completeness due to this countable collection, which we did not require in the previous theorem. So equivalently, you can another way of saying in terms of nowhere dense sets is that if you have a countable collection of nowhere dense sets, then the countable union of nowhere dense closed sets is nowhere dense in X. Okay, so this is an alternative equivalent statement of the Baire category theorem. So what is the proof? Something similar to the previous theorem, the proof, but now we have a countable collection, so we have to do a limit process unlike the previous finite collection. So you start with an x naught and you start with an epsilon. We have to show that the epsilon ball around x naught intersection u is not empty. That's what means when you want to say u is dense, you need to show this. So since u1 is dense, we choose a since u1 is a dense set, we choose an x1 in x and epsilon 1 which is less than 1 such that this closed ball is contained in u1. Okay, this is by the density of u1. Similarly, you choose an x2 and an epsilon 2 which is less than half. So earlier epsilon 1 was chosen less than 1, now epsilon 2 is chosen less than half, such that this closed ball centered at x0 with radius epsilon 2 is contained in u2 intersection this. Okay, this is again by the density of u2. So you proceed like this. So if you proceed in this form, then you actually have a sequence of closed balls centered at x1, x2, x3, so on, and you have and the radius of these balls are decreasing sequence converging to 0, right? Because they are all less than 1, they are all epsilon n is less than 1 over n. So you have a nested balls here, right? Decreasing sequence of balls. Yeah. So now what you do, now for any n naught, you choose m comma n which are bigger than n naught. Okay, now because m comma n is bigger than n naught, 1 over m is less than 1 over n naught, 1 over n is less than 1 over n naught, what we have here. And by our choice, by the way we chose the sequence, epsilon m were less than 1 over n and epsilon n were less than 1 over n. So using this property, we see that if you look at the distance between dxm by distance between xm and xn by triangle inequality, this is distance between xm xn naught and xn naught xn. This is by triangle inequality for where this n naught is chosen like this, right? M and n are bigger than n. Now, because of the fact that m and n are bigger than n and bigger than n naught, and you have this nested property here, so epsilon the epsilon m and epsilon n balls are actually contained in the epsilon n naught ball, right? Because n naught is bigger than n naught is smaller than m and n, right? So you have that n naught is smaller than m and n. So these ball of the radius epsilon m and epsilon n is contained in epsilon n naught. So this distance is actually less than epsilon n naught. This is epsilon n naught. So 2 times epsilon n naught, but epsilon n naught is 1 over n naught, so this is 2 over n naught. So distance of this is given is less than 2 over n naught, where m comma n is greater than or equal to n naught. So this can be made as small as you want, right? So what we have shown here is that the sequence xm that we have obtained is actually a Cauchy sequence. But now we are in a complete metric space, so this Cauchy sequence should converge, so it should converge to some, and that element is in X. And if it's a convergent sequence with the same argument as we have given here, for all n bigger than or equal to n naught, xn belongs to b epsilon n naught xn naught, right? Because that's how we have, because n naught is less than n, so the ball of epsilon n naught is bigger than the ball of epsilon n here. So xn is actually contained in b epsilon n naught xn naught. Therefore, the limit of the sequence x should be in the closure of this ball, So x belongs to this closed ball. But this closed ball for each uh, I is contained in ui intersection b epsilon x naught. This is by our construction. This is true for all, because this is the first ball, right? So this is true for all I. So therefore, if you do the intersection, x belongs to u intersection b epsilon naught, intersection of all these, right? So this is the proof of that result. By this we have shown that u is dense in the capital X. So what is Baire category theorem actually saying is that it's actually saying that any complete metric space is second category, right? What we have shown is that when you have a complete metric space, the countable intersection of dense sets is dense, right? Which is precisely the statement complement to first category. So any complete metric space is second category. So this is the statement of Baire category theorem. Now let us look at some consequences or corollary to the Baire category theorem. So if X is a many metric space which is countable, so if a metric space is a countable union of closed sets, then if the interior of the closed sets is empty, then X is not complete, and if the metric space X is complete, then one of the closed sets should have a non-empty interior. All of them cannot have empty interior. In fact, these two statements are same, right? This is so these two statements are kind of same. So I'm just giving that together. So what is the proof of this? So suppose say the given metric space X is a countable union of closed sets. Okay. Now, if ever if X is a complete metric space, the statement here, and each GI is closed, right? Then UI, which is the complement of GI, is an open set. Okay, it's an open set, and the fact that the union of GI is X means the intersection of UI is empty. So UI is an open set, and its intersection is empty. Now, since intersection of UIs are empty, which means intersection of UI is not dense in X, right? And since X is a complete metric space, it means that not all of the UIs are dense. There's at least one UI which is not dense, because if all of them were dense by Baire category theorem, this should be dense, so it can't be empty. So at least one of the UI is not dense. And for that UI, if you look at the complement which is GI, I mean, which if you look at the interior of the complement of that UI, that is non-empty because they are not dense. Okay, so that's the proof of this. So this is also easy to see. The interior is empty, then X cannot be complete again by Baire category theorem. Now let's look at some example corresponding to the previous corollary. So if you notice that all the rationals in the real line are actually countable union of nowhere dense closed subsets. So Q cannot be complete metric space. If you give the usual metric here on Q cannot be a complete metric space at all with that metric, because Q can be written as a countable union of nowhere dense sets, whereas by Baire category theorem, the complete metric space should be second category. The other example is for the second part that we proved, that for something like say R2 cannot be written as a countable union of lines. So in this case, we know that R2 is actually a complete metric space, and R2 cannot be written as countable union of lines because line is actually a empty interior set. It's a set with empty interior. So if one can write R2 as a countable union of it, union of lines, then it contradicts the fact that by Baire category theorem, it contradicts the fact that R2 is complete. Now the same argument is valid for actually any Rn. Now, other consequence of Baire category theorem is this, that in a complete metric space, the intersection of any countable collection of dense G delta set is also G delta. What is a G delta set? G delta set is the uh, countable intersection of open sets. So if you recall the definition of topology or topology in topology, it says that it has to satisfy some three conditions. One of the conditions is that the arbitrary union of the sets should be contained in the collection, and uh, finite uh, finite intersection should be contained in the collection, right? So these are all open sets, right? That's what we call open sets. So here we are talking G delta sets. Basically means it's the G delta set is a countable intersection of open sets. So in a complete metric space, again by Baire category theorem, any countable collection of G delta sets is also a G delta set, because every G delta set is a countable intersection of uh, open sets, right? Open sets. So if if you have a dense G delta set, so they are dense open sets. So you you actually have that this G delta set, the countable collection of G delta set, is actually a countable intersection of uh, open dense sets, right? So this has to be dense by the Baire category theorem. I have just said that proof is trivial because G delta set is a countable intersection of open sets. Now, another consequence of Baire category theorem is that whenever you have a complete metric space with no isolated points, then any countable dense subset of X cannot be a G delta set. So let's start with the contradiction. Let uh, let E be the countable dense subset of X. Okay, we need to show that it cannot be a G delta set. So let E be a countable dense subset of X, and suppose E is G delta set. So it's a G delta set means it's a countable intersection of open sets. So E is a countable intersection of open sets. Since E is dense, because it's a countable dense set, since E is dense, this UI is also dense, right? Again, by the Baire category theorem, right? So UI is dense for all I. Then the set Vi, which is UI removed all the points up to Xi. Okay, so UI remove this, so this is also dense because intersection of Vi is empty and this is not dense in X. Right? So now that contradicts the Baire category theorem because these are also VIs are also dense subsets and open in X by this definition itself. This is open and dense. You are just removing some finite number of points. So Vi is also a dense open set. That is where we have used the fact that X has no isolated points. So the points that is being removed are actually not the isolated. It doesn't have it. I mean, they are not isolated points. So Vi is also a dense subset and open in X, but intersection of Vi is empty. Why? Because intersection of Vi is precisely intersection of Ui over and union of all this, which is E. So this is actually empty. E is equal to intersection of Ui. So this contradicts the Baire category theorem because you have a dense collection of open sets whose countable intersection is not dense. So which means that our assumption that E is a G delta set is wrong. So you cannot have a countable dense subset which is G delta. Now let's do another important rule, which is the uniform boundedness principle. The uniform boundedness principle tells you that if you start with a complete metric space X, and if you look at the space or set of all continuous functions on X, it's a real valued continuous functions on X, and if you take any subcollection of the space of continuous functions, then you have the following two possibilities. Okay, if you take the supremum of F over the collection that we have chosen, then this is unbounded, that this is infinity for all X in some G delta set. So there is a G delta set of X, and on that set, and for all X in that set, you take supremum. So here you see X is fixed, so X is coming from a G delta set. So for all X in the G delta set, supremum over the F, the subcollection, is actually infinity. The other possibility is this, that there is a M and an R and an X naught such that supremum, that is supremum over all X in a ball of radius R centered at X naught, and supremum over all F in the subcollection. So you see this supremum is over the variable X, this supremum is over the function F. So you take supremum over all this subcollection and supremum in this ball of radius R, and this is bounded by some M. So there is an M, R and X naught such that supremum in that ball of centered at X naught radius R and supremum over all subcollection is bounded. So this is uniform boundedness principle. So uniform boundedness is precisely for this reason. So the supremum, this M is So the supremum is over both the f and x, right? It's a uniform supremum. So they are uniformly bounded. So what is the proof of this? First, you define a fn, if a set fn, which is set of all x, such that supremum of f mod f of x is less than or equal to n. Okay, so we need to show this or this. So we start with this definition and look at all x such that supremum of f mod f of x is less than or equal to n. Now by definition, if you note, this fn is intersection of f inverse of minus n comma n. So it's inverse image of the interval minus n comma n, an intersection over all f. Right, so because supremum over all f less than or equal to n, mod f of x less than or equal to n. So basically you take the interval minus n comma n and look at the inverse image of under f, and you take an intersection over all f in the subcollection. So this fn is same as that. Now because f is a continuous function, this is minus n comma n is a closed set, it's inverse image of closed set, so this is a closed set, and this is arbitrary intersection of closed sets, which is a closed set. So fn is a closed set. And also fn is an increasing sequence of closed sets, right? Because f1 is contained in f2, because f1 is related to minus 1 comma 1 inverse image, whereas f2 is related to minus 2 comma 2, which contains minus 1 comma 1 interval. So you have this nested property of these sets capital Fn's. So then you can define the union of Fn. So this is a countable union of closed sets. Countable union of closed sets is called a F sigma set, similar to the countable intersection of open sets is G delta set, and countable union of closed sets is a F sigma set. So from here we have obtained that F, capital F, which is union of these Fn's, is an F sigma set. So now there are two possibilities. One, F could be a first category subset of X. If this capital F is a first category subset of X, and since X is complete, by Baire category theorem, the complement of this first category set should be a dense G delta subset of X. Okay, and further, if you take any X in F complement, what is F complement? F is union of all Fn. Fn is all these set which is bounded by n. So union of all that, which means it's bounded by each Fn is bounded by n. So union of all that is bounded by all possible n's, right? For each, the union over that. So complement basically means that any element in the complement will basically mean that supremum over this is infinity, because all boundedness is included in the F case. So from here we get the first property. So if F is first category set, we get the first property. If F is not first category, then it's second category. If it's second category, and since X is complete by again Baire category theorem, because F is now a countable union of F sigma sets, so there is a number m such that one of the elements in the union, let's call it Fm, capital M, has non-empty interior, right? Because if they are all empty interior, then this is a countable union of nowhere dense sets. Okay, but X is a complete metric space, so that's not possible. So one of the Fm's in the union should have non-empty interior, which means non-empty interior means there is an X naught in Fm and there is a ball, there is a radius uh, r greater than 0, such that this entire ball centered at x0 is contained in Fm, because of the non-empty interior mean there is an open ball contained in that. Now this precisely is the statement we have here, right? Why? So we need to show that this is supremum of over the ball and supremum over the family is less than n, and that is how we have chosen, right? So when you say this Baire x0 is contained in Fm, Fm is precisely this. Fm is precisely set of all x such that supremum of this is less than or equal to capital N. So this part is already taken care of, right? And when you say Baire x0 is contained in Fm, so supremum of that over that ball is also contained in N, because this entire bigger set is contained in N. Set of all x. So this Baire x0 is a collection inside this S capital N. So we have, that way we have shown both these properties. So we have shown the Baire category theorem, and we have shown some of its consequences and kind of useful corollary, and we have also seen the uniform boundedness principle. Okay, this is purely in the topological setup. Okay. Okay. Okay, thanks. See you in the next lecture.